Welcome to Year 2, Pure Chapter 6, Trigonometric Functions. We're going to discover 3 new trig functions. You thought you knew everything there was to know about how many trig functions there were. Well, you're already familiar with these 3 main ones. You choose 2 sides of a right-angled triangle, you divide one by the other, and out pops the ratios sine, cos, and tan. However, if you choose 2 sides from the 3 sides of a right-angled triangle in order, and then you divide them, there are actually 6 different ways you can do this. Instead of just opposite over hypotenuse, you've also got hypotenuse over opposite. And we have hypotenuse over adjacent and adjacent over opposite. That gives us these 3 trig functions. These are sometimes known as the reciprocal trig functions, and that's how I'll usually refer to them. They are not the same as inverse trig functions, although annoyingly notation with trig is all over the place, so you've got to be a little bit careful. When you see sine to the minus 1, that is the inverse function. It reverses the sine function. This that we're looking at now, on the other hand, this is the reciprocal of the sine function. It doesn't do the opposite, it does the reciprocal. So if you multiply sine theta by cosec theta, you will get 1. So it's a multiplicative opposite as opposed to a function inverse. Now you might be wondering why we're looking at these in the first place. Clearly cosec, sec and cot are not completely new. They are derived from just a different way of combining the opposite, adjacent and hypotenuse, and the reason you've never needed them before is that if you're having to solve an equation involving adjacent and hypotenuse, sometimes you have to divide things or flip things over. They are the reciprocals of the 3 functions you know. This is also why it doesn't appear on your calculator anywhere. You don't need to, because you can do 1 over cos or 1 over sine. It's worth looking closely at the words, where they come from. Just like cos, sine and tan, they are short for longer words. Cos is the cosine, so it's the complementary function that goes along with the sine function. That's why cosine of, say, 50 degrees is the same as sine of 40 degrees. They work with the complementary angle. The angles that add up to 90, one of those will have a particular value when you put sine, and the other one will give the same value if you use cosine. Tangent is the one that behaves a little bit differently. The cotangent of the tangent function is also the reciprocal of the tangent function, whereas the cosine of the sine function is different to the reciprocal of the sine function. A good way to remember which of these is which is to notice that the one that begins with an S goes with the one that begins with a C, and the one that begins with a C goes with the one that begins with an S. The only one that breaks that rule is cot, but that ends in a T. So some people will use the fact that sec ends in a C and sec is the reciprocal of cos. Trouble with that is, of course, cosec also ends in a C. Cot at least ends in a T, and that's the beginning of tangent. So if you remember that cot is short for cotangent, that's going to make life a bit easier for you. But sec and cos go together, cosec and sine go together. You might be wondering why we use these at all, or where they come from. Originally, the reason we have words for these things, instead of just using 1 over sine of something, is that it wasn't always as straightforward as it is today to do 1 over a number. And so navigators and mathematicians, astronomers, would use a table of sines, tangents, secants, just like they have tables of logarithms. It wouldn't just be sines, cos, tan. They would need all of these other various trig functions as well, including a bunch of others like the versine and all sorts of other weird combinations, things that came up commonly in calculations, which is why they're still useful today, because they crop up a lot when we're doing calculations, equations, calculus, etc. with trig. They appear commonly, and therefore they need calculating quite often if you're doing things like navigation, and it wasn't particularly straightforward in the past to calculate directly. Okay, so just to clarify, the few things that you want to be aware of as you're working through this: the purpose behind it, even though we don't need them in the same way that people used to. Trig equations and trig identities can get very complicated if you have to constantly have fractions of trig functions. It can be harder to see and get a handle on how to manipulate them and deal with them. So we can make life a bit easier for ourselves if we do that. It basically means there'll be fewer fractions kicking around. But also, we're mathematicians. We don't have to have a purpose behind something to find it worth investigating. And these are interesting functions in their own right. If you've amused yourself by playing around with different versions of trig functions in GeoGebra, well, now you've got some more to think about. We can consider what happens when you do the reciprocal of functions that you know and love, and you'll find all sorts of other interesting patterns. There are some fascinating things that these functions involve behind the scenes. If you're curious about the geometrical context for these, I was going to put a link in here, but it's probably easier if you're just watching this by video to go to Google and search for what I searched for. Unit circle, 6 trig functions, GeoGebra. There's quite a few different versions, and you might find there are different ways of representing this on a unit circle, but I think this one is one of the most elegant ones, and you can see as you move things around how the tangent and the cotangent complement one another to some extent. As one gets big, the other gets small, and vice versa. And the same thing happens with the cosine and the secant, and then the sine and the cosecant. But I'll leave you to mess around with that in your own time. We're going to move on to drawing the graphs. So the first thing I'd like you to do, and you may find that it's useful to pause at some point and have a go at the tasks that I'm setting here. I'm just going to carry on regardless and assume that you can do the work and then carry on watching when you're ready. I'd like you to draw the graphs for sine, cos and tan. Draw them on separate axes the way I've done down here. Mark on the key points so that it's clear where the maximum and minima are, and any crossing points on the x and y axes. Then what I'd like you to try is sketching cosec and sec and cot, but you're going to do them on the axes that are most relevant for them. One thing I want to mention here is that cosec, occasionally you will see written like this, CSC, as opposed to COSEC. I think that's just because people like to have a 3-letter abbreviation for it in the same way they do for others, and using the first 3 letters just wouldn't work for obvious reasons. Hopefully you've had a chance to try that. If you think about how you can draw the reciprocal graphs, you'll find these points useful, I hope. The reciprocal of 1 is 1, which means if you're doing 1 over sine x, when sine x equals 1, you get 1. In other words, the point at the top of this graph will also be on the cosec graph. And a similar thing happens when you're drawing the sec graph on the same axes as the cos graph. You'll find that at 0 and at 2 pi, we've got 1 for cos x, therefore we'll have 1 for sec x. That will also happen on the tan graph. It's less obvious where it occurs, but there is a point at 45 degrees, or pi by 4, when tan gives a value of 1, and there'll be another one at 5 pi by 4. So if you've got a good eye, you can figure out roughly where those should be. They will be places where the trig function that you know and the new trig function that we're drawing, the reciprocal one, cross. But they're not the only places. Are any other numbers self-reciprocal? Turns out, yes. The number -1 works. If you do 1 over -1, you get -1. So that means we can find an additional point on this graph, and an additional point on this graph, and a couple of additional points on this graph. This will probably be something like 3 pi by 4, and whatever this one is, 7 pi by 4, something like that. But we can go a bit further. There's more you can do. The sine graph goes between 0 and 1 and -1. And therefore the reciprocal will go from 1 over 0 to 1 over 1 to 1 over 0 again, and then 1 over -1, 1 over 0. So we have to try to answer the question, what is the reciprocal of 0? And what is the reciprocal of infinity? That's going to be an issue when we get to tan. How do we do 1 over something which is both positive infinity and negative infinity at the same time? Turns out this is not as nasty as it seems. As you get closer and closer to 0, the reciprocal of your number gets closer and closer to, in this case, positive infinity, if we're at sine x, because we're getting closer and closer to 0 from above. So what we're going to end up with, and this can be a terrible diagram, but you'll be able to sketch these on GeoGebra yourselves, so I'm not concerned about the beauty of the diagram particularly. We have an asymptote at 0, and this thing curves down, hits the top, and curves back up, giving us another asymptote at pi, comes back up here from negative infinity, and then approaches another asymptote again at 2 pi. And predictably enough, the cosine graph, because it's a sine wave just shifted along, the secant and the cosecant functions, these two, will have similarities in the same way that cos and sine have similarities. So hopefully we can sketch this on. And if you're worried about the precision of your own graphs, hopefully my rough and ready versions here will set your minds at rest. Something like that. So if you do this for enough periods, you'll start to get a sense of what the function is doing. It shoots off to positive infinity, comes back from negative infinity, but never quite gets within the 1 to -1 range. So sine and cos are strictly within 1 to -1, and the reciprocal functions will be outside 1 to -1. Both sine and cos and sec and cosec touch 1 and -1, and that's the points, the only points where the graphs touch each other, but they never overlap more than at that point. Now we can do a similar thing with tan to get cot. When tan is 1, cot is 1, so we've got that point. But as tan gets smaller, cot gets bigger, and we end up with an asymptote for the 0. And that'll happen again for this one. We have a negative for the next one. We'll be approaching an asymptote towards negative infinity. So asymptote at 0, asymptote at pi, and then an asymptote again at 2 pi, approaching that way. So what happens in between times? As we do 1 over a larger and larger negative number, we get closer and closer to a smaller and smaller negative number. And from the other side, as we do this, well, now we can get a pretty good idea of what 1 over infinity should look like. You're probably guessing 0, feeling like it's a bit weird. I'll show you in a moment with a slightly different way of writing cot x why it's safe in this case to do 1 over infinity effectively equals 0. If you've drawn it even half as well as I have, then hopefully you've noticed that there's some lovely symmetry between the cot graph and the tan graph. And that's no coincidence. They are co-graphs in a sense. You'd have to reflect about, say, the x equals pi by 4, or various other places you can reflect, and you'll find that these graphs will end up being the same. You can reflect them that way, and there are all sorts of nice algebraic identities that correspond to the graph transformations you could do with these. Okay, so that's the graphs. Now we come to the functions themselves. We're going to think about their domain and range, and for this we start with sine, cos and tan, the ones we know and love, and we think carefully about what they do and refer back to your graphs, and it'll make life a lot easier. Just as a quick reminder, we have the domain, which is the values that go in, so that'll always be something involving x, and the range are the values that come out, and that'll always be something involving f of x, in this case cos x, if it happens to be cos x. I would encourage you to pause at this point if you've not tried the sheet that came with this, and give this a go, see if you can fill in your values. And bear in mind we're going to be in radians. Unless otherwise stated, there's no particularly good reason to not be in radians. Occasionally they'll throw in a question in degrees still, but it will be explicitly stated. So if it's never mentioned, you can assume we're in radians. That's because nothing in calculus works nicely unless you're in radians. Okay, assuming you've had a go at this, let's check these out. The domain for cos should be obvious, and the range for cos should also be obvious once you've made sense of which one domain is and which one range is. Any real value is allowed. You can do cos of anything you like. You can try it on your calculator if you don't believe me, big numbers, small numbers, you'll always get an answer between 1 and -1. The same is true for sine. Tan is a bit tricky. You have to think about all of the places where tan is not defined. Any number you could put in your calculator that it wouldn't let you do. So the obvious one is pi by 2, which is 90 degrees. But then if you jump up another pi radians, another 180 degrees, then you get to another asymptote. So you can jump forwards or backwards as many multiples of pi as you like. If we start by mentioning one of the obvious asymptote points and then add multiples of pi, then we can describe in one go every single point, every single x value for which tan is not defined. And that gives us the maximum possible domain for the tan function. The range, well, it makes up for the fact that it has a slightly restricted domain by having a range which is not restricted at all. Any number can come out of this. You can get anything you like because it goes all the way up to positive infinity and all the way down to negative infinity, and of course everything in between. Now for sec x. Sec is the reciprocal of cos, which means we can think about what numbers can go into sec by considering what numbers can go into cos, but we also have to be a little bit careful. The times when sec does crazy things, just because cos is well defined doesn't mean sec will always be well defined. Looking at the graph will help you with this. Just like tan has asymptotes whenever sine over cos is undefined, well, that happens when cos is 0. And for the same reason, when 1 over cos is undefined, well, that happens when cos is 0 as well. It turns out the domain for sec is identical to the domain for tan, and for the same reason. Sec x is 1 over cos x. If the denominator is 0, we have a problem. Cos x is 0 whenever we get to pi by 2, 3 pi by 2, 5 pi by 2, etc. Negative pi by 2, negative 3 pi by 2, and so on and so on. The range is the exact opposite of the range for cos. You can have a go at writing this in different forms, but I think the laziest, easiest way is to write it as f of x is greater than or equal to 1, or f of x is less than or equal to -1. Now cosec and cot also share something in common. Cosec is 1 over sine, and cot is the opposite of sine over cos, which means it's cos over sine. They both have a sine x in their denominator. Therefore, there's going to be a problem whenever sine x is 0. So the domain for cosec is anything which is not a multiple of pi. Sine is 0 whenever it hits a multiple of pi. 0, pi, 2 pi, etc. And therefore, cosec will be undefined at 0, pi, 2 pi, minus pi, 57 pi, minus 32 pi, etc. The range is the same as sec, so it can be anything that isn't within the range -1 to 1, apart from the values themselves. And then for cot, we get the same domain as cosec for the same reason, but the range it shares with tan, because it happily goes through 0, and it then goes up as far as you like and down as far as you like without any discontinuities in its path. Okay. The last thing I want to look at with this first video is new identities that we can now create from the new trig functions that we've got. I've already briefly alluded to this. Tan theta is sine over cos. Well, if we know that tan theta is sine over cos, pause the video and see if you can write an identity for cot theta, which is built just from sine and cos. Okay, hopefully you got something like this. If cot is 1 over tan, then it's the reciprocal of tan theta, which is the reciprocal of sine over cos. 1 over sine over cos is cos over sine. So you can see how tan theta's asymptotes correspond to cos theta's zeros, and cot theta's asymptotes correspond to sine theta's zeros. You might wonder why we would do this. Turns out often it's a more helpful way to think of cot theta. All that weirdness we had where we were trying to think about dividing 1 by infinity when we were drawing the cot theta graph, we wouldn't have had that issue at all if we'd thought of cot theta as being cos over sine. When we do cos pi by 2 over sine pi by 2, we get 0 over 1, which is perfectly well defined. 1 over 0 we'd have a problem with, but 0 over 1 is not an issue. That has a value, it's a nice well-defined value, its value is 0. So cot can have a well-defined value if we think of it as being defined fundamentally as cos over sine. And then the fact that it happens to be the opposite of tan, or the reciprocal of tan rather, is just a happy coincidence. Whenever tan is undefined, well, we can think of cot as being cos over sine. All right. Next, this is the second of the two trig identities that you already know. And from this one, similarly to the previous thing we've done, we're going to derive some more trig identities. This is the trick. Divide both sides by cos squared theta and see if you can create a new identity that connects tan squared theta and sec squared theta. Pause now and give that a go. When you finish that one, try a similar thing to create an identity involving cot squared and cosec squared. All right. This is what you should end up with if you divide through by cos squared theta. Sine squared over cos squared becomes tan squared. Cos squared over cos squared becomes 1. And 1 over cos squared is our newly minted friend sec squared theta. And the similar trick that I'm alluding to in the second part, we divide through by sine squared theta instead of cos squared theta, and that automatically turns the first term into a 1, the next term into a cot squared theta, and the final term into a cosec squared theta. Make a careful note of these identities, but remember it's not essential to memorize them as such, as long as you memorize and you remember the method for which we generate them. If you have sine squared and cos squared in your head, and then you know how you can turn it quickly into the other two, it becomes the work of a moment. As soon as you realize you're doing a trig question, or solving a trig equation, or dealing with a trig identity that involves sec, cosec, or cot, you can jot these things down, working them out as you write them down. I mentioned in a previous video we were talking about equations that involve cos and sine squared, or sine and cos squared, and we talked a bit about how the similar idea would work well when we get to these trig functions. If we have sec squared and tan appearing in the same equation, the fact that sec squared can be written in terms of tan squared means that this equation can turn into a quadratic in tan theta. So it turns into an equation that's just as easy to solve as the ones we had before. Provided you can see it the right way, you can break it apart and think of it as a quadratic that can be factorized, or you can complete the square and you can find solutions, in this case for tan theta initially and then for theta. Alright, tune in for the second video when you've had time to digest this and work on the worksheets that go with it.